Hi, I'm Yang from Stanford. Today I will talk about multimodal guidance for handheld tool movement in optics see-through AR. AR overlays can be really helpful in guiding tool movements, but in practice they suffer from depth ambiguity, lighting, and occlusion, which can reduce precision and trust. Our idea is to pair AR visuals with wrist-based vibrotactile feedback that gives directional and state cues, so that the user doesn't have to rely on vision alone. I will walk through the design, then the tool studies, where we conducted a cue recognition experiment and a tool guidance task. As a result, we showed that AR plus haptics improves precision and usability with a small time trade-off. AR overlays keep guidance in the operator's field of view, but relying only on vision can backfire in realistic conditions, especially with optic see-through displays. Users report issues like depth ambiguity, overlays that don't occlude correctly, and brightness or color that just make it really hard to judge alignment. That can increase cognitive load and make people second guess whether they're actually on target while holding a tool. Haptics is a great complementary channel because it is eye-free and doesn't add more visual elements. So our core design decision is to make the guidance cognitively manageable by guiding planar motion on a reference surface, like the kind of tool movement surgeons do relative to bone or skin, and provide separate cues for move up and down when the user drifts out of the plane while holding the tool. Before building the full system, we run a formative study with 12 participants to answer two design questions. First, how should the wristband define up for directional cues? We tested a wrist up mapping where the top of the wrist always means forward or up in the space, versus a tool-oriented mapping calibrated to the initial tool grasp. The strong preference was for wrist up, because it is consistent even when the tool rotates. Tool-oriented cues were often described as confusing because the reference shifts as the user changes orientation. Second, we asked what maneuvers matter most. Participants converged on a small set that we could encode clearly. That includes, first, a continuous planar movement, second, out-of-plane correction, including move up and move down, and third, two discrete states, pause and arrive. This slide shows the implemented system. The wristband has 12 vibrotactile motors spaced around the wrist so we can cover the full 360 degrees. To get smoother directional feedback than the 12 fixed points, we use phantom sensation, where we drive two neighboring motors with interpolated amplitudes so that the users feel a single virtual vibration direction between them. On the AR side, the head-mounted display sends commands to an Arduino board that controls motor actuation. We designed 5 cues. For planar movement, the vibration points you toward the target direction, and the pulse frequency increases as you get closer, mimicking urgency. If you drift out of the plane, we trigger move up or move down patterns using groups of actuators on the top or bottom of the wrist. When you return to the valid plane, you get a clear pause cue, and when you are within the arrival threshold, you get an arrived cue using all actuators, which was particularly designed to be highly distinctive. Our first study asked a fundamental question. If we add wrist haptics in an AR context, can people reliably interpret the cues? In experiment 1, participants were the wristband and HoloLens head-mounted display, and we played randomized cues. They verbally identified which category they felt: planar move, move up, move down, pause, or arrive. Recognition was high overall, but there was a clear pattern. Pause and arrive were recognized the best, around the high 90% range, while the directional cues were slightly lower in the low 90s percentage range. The takeaway is that all motors or multi-motor patterns are especially robust, while localized directional cues require a finer discrimination, which are still good, but more subject to false recognition. That informs design of using highly distinct patterns for critical state changes like arrived or stop, and keep directional cues simple. Experiment 2 tests the core claim: does multimodal feedback actually improve performance in a surgical-like targeting task? Participants used a knee phantom under surgical lighting. They moved a track tool to AR targets on a defined plane. We compared 3 conditions: haptic only, AR only, and AR plus haptics. The main goal is precision. AR plus haptics achieved the best endpoint deviation at 5.8 millimeters, compared with 9.3 millimeters for AR only and 15.1 millimeters for haptics only. So the combination clearly improves spatial precision. For speed, we see a trade-off that AR only was fastest at around 6 seconds, while AR plus haptics took around 8 seconds. Haptic only was slowest at about 15 seconds. Subjectively, the combined condition also performed the best, where the workload was significantly lower, and the usability was highest with system usability scale around 88. Qualitatively, participants described AR as helpful for getting close and haptics as providing reassuring confirmation that reduced second guessing, especially under depth ambiguity in optic see-through displays. In conclusion, we show that wrist-based vibrotactile feedback can meaningfully enhance AR tool guidance. The combined AR plus haptics condition achieved the best precision and the best usability, and it also reduced workload, although it caused a modest increase in task time compared to AR only. A useful way to think about it is a division of labor where AR provides global spatial context, while haptics provides local correction and confidence, especially near the target. Design-wise, a stable wrist-based mapping worked better than an adaptive tool-based one, and distinctive multi-actuator cues were the most reliable for state changes like pause or arrive. Looking ahead, we want to validate in more realistic clinical settings.